Well, we've made it past nuclear chemistry, and now we're going to be talking about the history of the discovery, of the three subatomic particles within the atom. We're going to make a connection to nuclear chemistry at the end of this video. So we're going to begin with the discovery of the electron. To remind you, the three particles, subatomic particles that make up the atom: the proton with a positive charge, the neutron with a neutral charge, and the electron with a negative charge. And J.J. Thomson here discovered the electron. And so let's talk about that in a little bit more detail. I'm not sure why it's not changing like it's supposed to. There we go. He was an English physicist, and again credited with the discovery of the electron, and he used a piece of equipment called a cathode ray tube. And I have one of these in my classroom, although it's inoperable. If I can find the video, I'll link it here to your Google Classroom. So essentially, if you've ever seen one of those giant boxy televisions, it used something similar to a cathode ray tube to produce the picture on the screen. If you've ever, if you were at your grandparents' house and they say that the tube blew up or stopped working in the television, they were talking about this glass device here. So he used this to discover the electron. He did it in such an interesting way, essentially using a magnet. This cathode ray tube, well, actually, let me see if this slide talks about it. Yeah, when two metal plates inside this thing are connected to a battery, the negatively charged plate, called the cathode, emits radiation. In other words, when you hook this cathode ray tube up to a battery, it produces radiation, which again we've talked about in the previous video, except obviously this isn't, hazardous radioactive stuff. And these rays that are produced are called cathode rays. And what's so cool about that, Thomson realized if you placed a negative charge close to this ray that's produced inside this tube, it deflects. But if you placed a positive charge close to it, it attracted it. So let's think about that. There's a saying that we all know, that opposite charges attract and like charges repel. And so because Thomson placed a plate with a positive charge and the ray was attracted to it, that must mean the ray, the beam or the rays, whatever they're made up of, were negatively charged particles. And so that is what led J.J. Thomson to understanding that the electron had a negative charge. These cathode rays that were produced were streams of electrons. And when he realized something with a positive charge was attracting these electrons, he realized he had discovered they had a negative charge. So J.J. Thomson discovered the electron, which had a negative charge, with something called the cathode ray tube. And notice the year 1897. So, we knew atoms were a thing all the way back from Democritus. And then John Dalton reaffirmed Democritus' theory. But it wasn't until 1897 we started actually learning more about the atom. And the electron, as you'll find in this class, is the core of chemistry. In fact, really from now on, we're going to be talking about electrons. And you're going to realize that one electron moving changes the world. And it's quite the quest, and I'm glad you're along that journey. So next we got Robert Millikan. Robert Millikan, now again, J.J. Thomson discovered the electron, and he knew it had to have a negative charge because of the design of the cathode ray tube. But this dude here, Robert Millikan, who I call the milkman, he discovered the magnitude of the charge of the electron. So I don't want you to be confused. J.J. Thomson knew the electron was negative, but Robert Millikan said, hey, the charge is exactly negative 1.6022 times 10 to the negative 19th. And that unit's called the coulomb. Don't worry about it. I'm not necessarily wanting you to become familiar with it, although you should understand that number is written in scientific notation. And Millikan discovered the magnitude of the charge of the electron by using something called the oil drop experiment. And again, I'm not so concerned that you know how this experiment worked as much as I want you to know that Millikan discovered the magnitude of the charge of the electron. And so here's the deal. This is 1897 when J.J. Thomson discovered the electron using the cathode ray tube. And then we got 1910 when Robert Millikan determined the magnitude of the charge. And so, we're at 1910, and this is what we thought the atom was like. Well, we knew that we had negatively charged electrons, but the problem is scientists had known for a long time that the atom was overall electrically neutral. And so think about that. If we know there's a negative charge, but we know overall the atom is neutrally charged, there's got to be a positive charge somewhere in the atom. So scientists knew as a result that there had to be a positive charge somewhere to counteract that negatively charged electron. And so they started looking for it. But it took a while for them to discover the proton. And so at the time of this slide, the proton hadn't been discovered yet. They just knew that there was some substance or some particle inside of the atom that counteracted the charge of the electrons. And so J.J. Thomson came up with this model here called the plum pudding model. This is modeled after a dessert that's popular over in the UK. And so here's what J.J. Thomson fashioned the atom to be like. Again, this is before the discovery of what that positive charge actually was. So he fashioned it as such. You see the raisins inside this plum pudding cake here? So he said, well, the electrons in the atom are like the raisins in this plum pudding here. That represents the negative charge. But the dough or the bread of this plum pudding represented this goo of positive charge that was counteracting the negative charge of the electrons. And so he was like, well, the raisins are evenly distributed throughout the dough or the bread, which again represented the positive charge, and that is what caused the atom to be overall electrically neutral. And of course we know this not to be true now because we know that the proton exists, but at the time they didn't. So this is called the plum pudding model, and the key phrase is equally distributed. That is, he felt the electrons or the raisins were equally distributed throughout the bread or the dough, that is the positive substance of the atom. That's the plum pudding model. But guess what, friends? Ernest Rutherford was the guy who discovered what that positive charge actually was, and of course that is the proton. Notice that Robert Millikan discovered the magnitude of the charge of the electron in 1910. And then that's when Thomson came up with his plum pudding model of the atom. And 1 year later, in 1911, the mystery of that positively charged particle had been broken. Again, Ernest Rutherford discovered the proton in 1911. But how did he do it? It's through an experiment that we'd call the gold foil experiment. And here's how it works. He directed alpha particles, which is just a relatively harmless form of radiation for your information. So he directed alpha particles at very thin sheets of gold foil. Think of aluminum foil, but made out of gold. And of course, you would figure that because the gold foil is so thin, that you would figure 100% of those alpha particles would go straight through it and wouldn't be deflected at any sort of an angle. He figured they just go straight through and, you'd be able to see that. But here's the problem. Only the majority of the particles went straight back. Every now and then, one of the particles would be scattered at a large angle. And as you can see, he figured that he would direct these alpha particles to the gold foil, And again, he figured that they would, 100% just go straight back, right? And for the most part, you can see most of the particles do go back straight through the foil. However, a few particles are slightly deflected and a few are significantly deflected. And the problem is, through his calculations, they should have all passed straight through and none of them should have been deflected at any angle whatsoever. And so the question naturally becomes, well, what's causing this? The answer is the proton. Because we know now that the atom has a nucleus. And and the nucleus is in the center of the atom. And now we know that inside that nucleus are the protons and the neutrons. What was happening is, when these alpha particles were being shot at the gold foil, every once in a while, instead of just going through the empty space, which is what atoms mostly are, every once in a while, the alpha particle would hit dead center of the atom and would be deflected by the nucleus, again, which contains the protons. And so that's the deal. Every once in a while, these alpha particles would be deflected once they hit the nucleus of the atom, which of course contains that mystery positively charged particle called the proton. So again, Ernest Rutherford discovered the proton, and the nucleus for that matter, using the gold foil experiment. And so in the plum pudding model, the positive charge is diffuse, that is, equally distributed. And Rutherford found that the alpha particles close to the center were deflected. And again, that what this slide is saying is what I just said, that the protons in the nucleus and those alpha particles would occasionally hit the nucleus, causing them to deflect. And what's an interesting thing is there were two undergraduate students who were there with Rutherford at the time of his discovery. I know you're not in college yet, therefore you're not an undergrad, but it doesn't, I put this slide in there to help you to understand that yes, even young people can be involved with major scientific discoveries and breakthroughs. And that's you. And you're in that generation, and there is nothing you can't do if you don't set your mind to it. Think about it. With all the technology that we have now, you have the world at your fingertips. These folks were roughly your age, and they didn't have all that, yet they were able to help achieve this breakthrough. And so there's no telling what you can do in your lifetime. And then finally, there's the third subatomic particle, the neutron, and it was discovered last by a guy named James Chadwick. And how did James Chadwick discover the neutron? Well, it's through what we call the weight problem. And if you think about it, it makes sense that the neutron was the last particle to be discovered, because what charge does it have? A negative charge, you're right. And at this time, they knew that the atom had an overall neutral charge. So their mentality was, hey, we've discovered the positive charge, we discovered the particle with the negative charge, and so there's probably nothing else to discover until James Chadwick ran into this weight problem. Here's what I mean. It was known that hydrogen, the simplest atom, contained only one proton, and that helium, the second simplest atom, contained two protons. That is, the atomic number of hydrogen is 1, as you can see here, and the atomic number of helium is 2. And so you would surmise that the mass of helium would be exactly double that of hydrogen, because it has, well, at least they thought it had, double the particles. But guess what? That's not the case. In fact, it was determined that helium weighed 4 times that of hydrogen, even though it allegedly only had double the particles. Here's the deal. I don't care that you know how Chadwick discovered the neutron, But here's what you need to understand. The discrepancy in the weight was because he found these tiny particles called neutrons, and those affect the mass of the atom, right? And so because helium weighs 4 times more than hydrogen, well, it's because it's got more neutrons than hydrogen does, and that increases the mass. So this discrepancy in weight led James Chadwick to understand, hey, atoms have neutrons. They have a negative charge, but they do affect the weight of the atom. And by the way, the neutron, along with the proton, make up the nucleus, so it's in the center of the atom, whereas the electrons are up in the electron clouds. But believe me, it's not that simple, and we'll get to that. All right? And again, they have a neutral charge. Now, one thing that I want you to understand, each atom can have, well, let me say this way. Atoms of the same element can have different numbers of neutrons. And we call that an isotope. And so, like carbon. Well, carbon has a certain number of protons and a certain number of electrons. But it can have varying numbers of neutrons. You could have carbon 12, carbon 13, or carbon 14. And what determines which one it is the number of neutrons in that atom. And we call those isotopes. So isotopes are atoms of the same element, but with different numbers of neutrons. So again, carbon has 6 protons, 6 electrons, providing that's not an ion, but it could have different numbers of neutrons. And we call that an isotope, right? And that does affect the mass of the element. Because again, I told you, every time you add a neutron, you are affecting the weight. And that's how James Chadwick was able to discover the neutron due to that weight discrepancy. In this picture here are the 3 isotopes of the element hydrogen. Hydrogen with 1 neutron is called protium. Hydrogen with 2 neutrons is called deuterium. That is what makes up heavy water, by the way, if you've ever heard of heavy water. And hydrogen with 3 neutrons is called tritium. And again, that affects the mass of the element. But these are all still hydrogen atoms. So we call those neutrons. So just a quick review. Changing the number of protons changes the identity of the atom. So, the element with 1 proton is hydrogen, the element with 2 protons, helium, so on and so forth. So the result is a completely different atom. If we change the number of electrons, it just affects the charge. So, if you got 1 electron, well, you got a -1 charge. If you have 2 electrons, you have a -2 charge, so on and so forth. We call those ions. If we change the number of neutrons, you just change the mass, and atoms of the same element that contain different numbers of neutrons, as we said, are called isotopes. And so I'm going to stop this PowerPoint here, and we'll pick up on this later when we talk about percent abundance and how the mass of the elements on the periodic table are calculated. Have a great day.